Okay, let's take a look at example program unit B4 page 7. This is very fundamental basic program for hydrostatic resultant force. Let's take a look at program here. So this is a large lake or some kind. This is a plane surface which happen to be 60 degrees of an angle from vertical direction. Okay. And then at the depths of 10 meters, you are going to have a circular cross-section gate, which is operated by this shaft located right in the middle. This is the centroid of this cross-section. Shaft just goes through the centroid. Okay. So this is the circular cross-section gate, which is free to rotate around this shaft. Okay. This is a water, so it's a given specific weight. So this gate is mounted on the shaft along its longitudinal diameter, horizontal diameter, sorry. For a water depth 10 meters to the shaft, determine two things. A, the magnitude and location of the resultant force exerted on the gate. Second one, B, the moment that would have to be applied to the shaft to open the gate. Okay. Let's take a look at the same exact picture on the whiteboard. Okay. So definitely this kind of program in general in hydrostatic resultant force requires a figure. So it's not a good idea, it's essential. You have to draw a figure for every single problem of unit B4 hydrostatic resultant force. So this is my figure. So let's try to understand the situation here. This is plane inclined surface which is submerged under, in this case, water. This plane surface has a 60 degrees of an angle as given. So first of all, we want to establish coordinate system. Coordinate system established is, first of all, y direction is in the direction of the plane inclined surface, which is y. And then x direction is, this is the x direction. This is the coordinate origin, let's call this point O. Okay. So x direction goes this way, y direction goes this way. That is the coordinate system. Okay. Now, however, sometimes I want to take a look at this particular gate from the direction perpendicular to this plane. So that's why I'm going to illustrate you. This is coordinate system, which is, this is x, this is y, is going to be rotated 90 degrees, showing you the cross-section of this gate. That's this coordinate. Okay. So from that perspective, this is the same point O. Now you are showing the cross-section of this gate by rotating this coordinate system 90 degrees. So this is x, this is y. Okay. So now you can see the side view of this circular cross-section gate. Right here is a centroid. This is the location shaft. All right. So first thing first, let's find out part A. What is the magnitude and location of a force? Hydrostatic resultant force developed by the hydrostatic pressure. Yes, of course. This location really means that location of center of pressure. Center of pressure here. Let's call this CP. Okay, so let's go back to this figure. center of pressure in this particular case is not going to be on the centroid of a given cross-section. By the way, let's just define the cross-section area you are interested in. This is the cross-section area. Let's call this A. Area of interest. Why do I want to call this area of interest? Because this is the area you are interested in finding how much force is developed on this area, which is submerged under the water, the centroid is located at the 10-meter depths. If you have this kind of area submerged under the water, how much force is developed? That's what you're interested in. So this is called area of interest. Anyways. So where is the center of pressure location? It's usually a little bit below centroid. So this is CP location. Center of pressure. And then this F1, hydrostatic resultant force, because it's developed by the pressure on the surface, it is always going to be the direction perpendicular to the plane surface and then acting through the center of pressure. So this is going to be F1. Resultant force developed by the presence of hydrostatic pressure. So this is a resultant force. This resultant force is going to act through the center of pressure, so it's going to act like this. And then you can determine also the magnitude. So let's determine the magnitude and the location, which is center of pressure, first. Okay? So of course we are going to apply the equation. Magnitude of the hydrostatic resultant force is PCA. Very simple equation. This PC is hydrostatic gauge pressure developed at centroid depths. That's PC. So that means, okay, so PC is gamma times HC. This is the centroid location, depths. So in this particular problem, where is the centroid location? Let's go back to here. This is the depth to the centroid. HC is 10 meters. You know that, it's given. Okay? So this multiplied by the specific weight of water, you're going to get magnitude of this F1. It's very simple deal. So this is going to be gamma of water times HC times area of your interest. Let's just go back and take a look. This is the area of your interest. This is A. Okay? So this is the water, so this is 9.8 kilonewton per cubic meter. Kilonewton is 1,000 newton per meter squared. So this is the specific weight of the water. Multiplied by depths is 10 meter depths to the centroid, HC is 10. Cross-section area is area of circle, which is pi over 4 times diameter is 4 meters squared. Okay? So this is a very, very simple calculation. You're going to determine the magnitude of hydrostatic resultant force, which is 1,230 times 10 to 3 newtons. This is a huge value. This is in fact 1.23 meganewtons. In fact, it's a very, very, very big force developed because it's 10 meters so much. So this is the magnitude. So where does that FR act through it, which is the center of pressure? So we are interested in the location of it. Okay. So location of the center of pressure measured from the surface of the water is this. This is YR. Alternatively, you can say depth to the center of pressure, HCP, or HR, let's say HR. So either depth or coordinate direction Y distance, either way is fine. But this comes with equation, is that right? So location of CP is YR. This one comes with equation. IXC over YCA plus YC. IXC this is the moment of inertia in the direction of X taken at the location of centroid. Let's go back and take a look at one page back. This IXC. You're going to go back to page 6 and take a look at IXC and IYC for the case of the circular cross-section. This is pi times radius to the force over 4. So this is a moment of inertia taken at the location of centroid in the direction X. In this case, direction X, direction Y is the same thing because it's symmetric. Okay? So let's just take this value. IXC is pi r force over 4. YC, this is location of the centroid. Location of the centroid is location of the shaft. This is a YC. Well, we do know HC. HC is 10 meters. We can convert Y from H using trigonometric relationship. This is a vertical depth, this is a coordinate distance, H and Y, related through angle theta, which is 60 degrees right here. Okay, so YC is, of course, this is going to be HC divided by sine of 60 degrees. So that's this YC. So YC is HC over sine 60 degrees. Okay? So we are going to plug in those and find out YR, which is, this is going to be pi times radius, which is 2 meters to the power of force divided by 4. YC is HC 10 meter divided by sine 60. Cross-section area is pi over 4 times diameter 4 meters squared plus YC again 10 meter divided by sine 60. Okay? So if you compute this, you are going to get 11.63 meters. So let's go back here. So you know this is 11.63 meters. So interesting thing about that is, well, you're going to have a small tiny difference here. This is the difference between YR and YC. Difference between centroid and center of pressure. Okay. So that's going to lead you to the solution part B. Okay, let's go back once again. Take a look at the problem statement. very closely once again. B. Okay. So program B is asking the moment that you need to apply to the shaft to open this circular cross-section gate. What do you mean by that? Well, you notice there is a mechanical stopper attached to here. So imagine yourself, this is a small tiny piece of metal which is welded to this surface, mechanical stopper. It is going to prevent this gate to rotate this way. So there's no way this gate is going to rotate this way because there's a mechanical stopper here. You can't rotate counterclockwise. You can only rotate in a clockwise direction to open this gate, which can naturally never happen because you are going to develop force here. This force keeps pushing this gate to this direction. So naturally, you can never open this gate. The only one way to open this gate is maybe attach the motor here to the shaft, apply the torque in this direction, clockwise direction. So you're going to literally apply a motor attached to the shaft, producing the torque in clockwise direction to open gate this way. So how much torque do you need, if so? So that must be a little bit bigger than the moment developed by the hydrostatic resultant force. Hydrostatic resultant force keeps applying the force like this. Multiplied by this much distance, you're going to calculate the moment developed by Fr, which is trying to keep this gate shut. So you need to pick up a motor which is stronger than that moment to apply in clockwise direction. So how much moment do you need? So let's take a look. Okay. The moment developed by F1 is obviously F1 times that. This is the momentum. Which is YR minus YC. So this small tiny momentum multiplied by F1 creates the moment around this shaft, which is F1 times YR minus YC. This is a moment created by this F1 and always trying to keep this gate closed. Okay? So in order to open this gate, of course you have to attach some kind of motor. And then if you turn on the switch, the motor produces the torque. That torque is opposite direction against this moment. Okay? And that moment must be stronger than this value, bigger than this value. Is that right? So let's find out first the moment developed by F1 is F1 times YR minus YC, which is magnitude of F1 is 1230 times 10 to 3 Newton. YR we found 11.63 meters. Subtract YC, which is 10 meter divided by sine 60. This is going to get you the moment. 102,083 Newton meter. Keep that in mind. This is the moment developed by F1. So your answer is like this. Okay? In order to open the gate, you need to attach a motor with larger than 102.083 Newton meter torque capable. So that your motor attached to the shaft is going to produce a torque in clockwise direction, which is opposite to this moment developed by F1, which must be larger than this value. Then you can turn on the switch of motor, then you can open the gate. Okay? Alright, that's it.